Hello, Mr. Steenerson here, and this lesson is going to focus on the kinematic equations. The first equation is a bit of a review, and is if we ever have a constant velocity, we're always going to use v equals change in x over time. The rest of the equations are going to focus on a uniform acceleration. So you have to determine those two things in first. A couple of quantities that for our uniform acceleration kinematic equations would be the initial velocity, final velocity, change in displacement, acceleration, and time. Any of those quantities we can solve for using the four equations that I'm going to talk about next. The first one is going to solve for our change in position, or our displacement. The next one is going to solve for our final velocity, our VF, given the initial velocity, the acceleration, and the time. Next one solves for displacement again using a different set of equations, and then finally VF squared is another final velocity. So why do we need four equations? Well, sometimes you're not going to be given some information in the problem, and so that's where this part of the chart comes in. You can definitely use this top equation if you have every variable except for acceleration. So if you're trying to solve for how far something's traveled, and you know the time, the initial and final velocity, you can use this if you don't have the acceleration. The next one you can use if you don't have a displacement, and you can kind of see the pattern here. The next one is if you don't have a final velocity, and the last one is if you don't have time. So all of these equations work together in order to solve for different variables of motion, and we're going to follow this basic pattern down here. We're going to make a list of our known unknowns, choose the equation that has the best fit, and find out what variable is being solved for. Remember, the acceleration due to gravity is downward, giving it a negative 9.8 meters per second squared for the acceleration. Okay, let's get started with the problem. We're going to try to solve how much space it takes for a jet to take off from an aircraft carrier. We're going to look at some information, write it down, list the variables, write the equation that best fits, rearrange those, and then answer with units. What I'd like you to do at this moment is pause the video, try this problem on your own, and then watch my solution. Okay, here's the solution for this problem. It says the Navy jet needs 2 seconds to go from rest to a speed of 170 miles per hour. Conveniently, I've told you the meters per second, so we want to make sure we're using the metric system. If that isn't the case, please convert. For this case, we're going to list down the time is 2 seconds, our speed is 75 meters per second, and we're looking for the distance, how much space does it take. Now be careful with this one. This is not a simple velocity is equal to the displacement over time problem, because we're accelerating. The jet is speeding up at a certain acceleration. It's not a constant velocity equation. So knowing that, we're going to write the equation, and in this case we're going to use the change in x is 1/2 times vi plus vf times the change in time. Rearranging, I'm going to substitute my values in, knowing delta x is equal to 1/2 plus 0 for the initial velocity, plus 75 meters per second for the final, times 2 seconds. This will solve then for 75 meters, which would be the answer for the distance traveled while this jet is taking off. Alright, in our next example, we're going to solve for the acceleration of that jet. So we're going to list our variables. The initial velocity is 0, the jet is starting from rest. The final velocity is 75 meters per second. And we are not going to use the distance traveled. I'm going to show you another way to solve this in the end using that, but just what's given, we don't know that. Acceleration we're looking for, and the time is 2 seconds. Our best equation for this case is going to be final velocity is equal to the initial velocity plus acceleration over that time interval. So we'll rearrange in this case for acceleration. So acceleration is equal to the final velocity minus initial velocity divided by the time. Substituting in the values I know, 75 meters per second is the final velocity, minus 0 divided by 2 seconds gives me an acceleration of 37.5 meters per second every second. Another way of writing this is the acceleration would be 37.5 meters per second squared. and you can see I'm using that indication on this example here. Now, of course, there is another way to do this. Once we've solved for that other variable, we could take another look at our knowns. I'll talk about that in just a second. But the last part here, I'm dividing this acceleration by 9.8 to show that the pilot is experiencing about 3.83 Gs. Okay, back to that other way of solving it. If we do use the information previously, and we know that the distance traveled was 75 meters, we can use a different equation. This one that is our Vf squared is equal to the Vi squared plus 2 times the acceleration over the distance traveled instead of the time. So this would allow us to rearrange, solve for A, and I'm going to get my Vf squared minus my Vi squared divided by 2 times the displacement. Okay. Solving again, substituting in, I get 75 squared, that's my speed, divided by 150. Solving that out gets me 37.5 meters per second squared. So there's two ways to find this acceleration. You'll often find that with the kinematic equations. You can solve them with one equation, substitute answer or values in, and you'll get the same answer with a different set of equations. Okay, for this answer, I'm only going to show you the solution. However, I would like you to make sure you list your variables in this section, write down the full equation, rearrange the values, and then put your answer with units. Doing all those steps, you should, in this case, get an acceleration that is a negative 33.35 meters per second squared. Now this negative sign becomes important in problems like this, and what it indicates in this example is that we're slowing down. Now that seems to be pretty in line with what we know and makes sense. If we have a negative acceleration, that means the acceleration is pointed to the left. So my vector would look like this. That's telling me the direction of the acceleration in this case. We'll talk about some other cases where a negative acceleration is not slowing down, but in this case it actually matches that intuitive quite well.